Okay, so let's start again. Last time we discussed, spatial stochastic model, right? To understand, population dynamics, right? Of population dynamics. And and this helped us make the, this helped us in two sort of ways. One, we were able to introduce, more realistic features, right? What were those? They were the fact that there is space, right? They were the fact that, the birth and death are stochastic. And we were also able to include processes like dispersal, right? Okay. Okay. So, it had basically more realistic features. And it also was different in the following sense. We were really defining very fine scale processes. Now, what were those fine scale processes? We were really talking about individual birth and death now. Whereas when we constructed models like logistic model or alley effect model, harvesting model, what we were doing was trying to write down population level descriptions. Okay, so whereas here we are really writing down rules of birth and death at the level of individuals. So they are actually individual level rules, right? Okay, now depending on how exactly you want to interpret 0 and 1, it could be an individual of it as a unit that is slightly more than an individual also. Okay, but I think it's individual level is one fairly reasonable description here. So it was different in these two ways, and we described these stochastic birth death processes. Okay, so what was that? If you pick two individuals randomly and they happen to be 0 and 1, and then there with probability P, there will be a birth event, or with probability P, the focal individual who's a could represent an organism will undergo death. Okay. Now here is the thing. Now, if I define the rules just like this, remember them. Carefully, recall what I just said. Now I said if you choose two individuals randomly, and if they happen to be 0, 1, meaning one of them an occupied site. Unoccupied. So of course, when I'm so I have to be a bit more precise. If we choose two locations in the space randomly, right? So this is the spatial system we have. If we choose two locations randomly, okay, that could be 0 and 1, and with probability P, it will lead to 1, 1. With that is not as choose an individual, right? Which, if it happens to be 1 in the neighborhood, give rise to a birth. So these two are actually fundamentally different models. Okay, so when we define a spatial model like the way in the last, we are really also paying attention to the location and the neighbors. So the 0, 1, or 2 randomly chosen individuals, but these are one is happens to be the first individual who's chosen, and if the neighboring site happens to be empty, then there will be a birth in the neighboring. Okay, so the space has to be considered appropriately here. Okay, that's the way we define the model. And then we also define this birth death process, which doesn't depend on the neighborhood at all. Okay, this was a simple birth death process. Now, to really understand what happens to the system with these type of stochastic birth death processes, uh, you know, one really needs to do what? Simulate. Okay, so we need to simulate these rules that I described a lot more carefully with every step in the previous class. Okay, uh, and you have to implement those update rules on, you have to create arrays to account for locations in space, and each array will have one of the two states, 0 or 1. Each array element will have one of the two states, 0 or 1, and then you iterate the processes of picking a site randomly, checking if it's occupied or not, and then applying these rules. Okay, and then we will find results. Okay, now, before we do, I explained that we can do something called a mean field approximation. Mean field approximation. The idea is that, okay, now these are all the rules happening at the individual level. Hey, but tell me, what's the likely population level behavior? So this is, you can say, average population behavior. Okay, so we can ask what exactly is the average population behavior, and then we define the rho as the density of the landscape. So density is basically could be thought of as a proportion of sites which are occupied. Okay, in this case, density is proportion of occupied sites. And we wrote down the master equation. So the general equation for two-state system was that dPA by dt was that, okay, there is some probability that the system is in state B and that state transitions to A. Okay. However, that's the gain of the density, probability in A. However, the state A also changes to state B. So this is effectively the birth of state A, whereas this is like capturing the depth of state A. Okay, the conversion. Depth need not mean a lack of. It just means that there is flow out of state A to B. Okay, so we considered P of 1. There are two states, right? P of 0 and P of 1 was nothing but rho, right? And P was 0, nothing but 1 minus rho. Okay, so now if we do, and then what we also did was we computed these transition rates. So this transition rate from 0 to 1, what was that? So if it is 0, it becomes 1 with probability P, that's the birth rate P, and then it also requires that the neighbor is occupied, and that happens with probability rho. Okay, and now what is P of 10? This basically represents the depth, and the depth doesn't depend on the density at all. So just 1 minus P. So if you now put all this together, we found an equation for rho. So if I remember correctly, I hope my memory works well. We got this. Was there a P there? P rho square. Okay, so we got this. This is the So this is the mean field theory or the mean field approximation. For the stochastic model. So what all does this approximation have? So basically it ignores two things. The funniest thing about this approximation is actually ignores two things we started off with, really wanted to include, right? It ignores space and it ignores stochasticity. Okay. So it actually ignores two novel aspects that we wanted to incorporate. Okay. But why do we do this? Because it actually helps make sense of what might be happening. You can think of it as, it actually provides some expectations when we actually do the numerical simulations. It shows that the phase diagram so looks like this. Between 0 and half, the extinction is the stable state. After half, the system, okay, has an active state where the density of state is non-zero anymore. Okay. So this is 1. Okay. So it shows that, when the birth probability is above a threshold value, which is half in this case, then the population will survive and will not go extinct. Otherwise, the population will go extinct. Okay. That's what this model predicts. Okay, now, of course, as we know, this is an approximation, right? Now, if you were to actually simulate the system and calculate rho star as a function of P, you might find something very different, by the way. There is no guarantee this will be true. Okay, but it provides a starting point for us to think what might happen in this spatial stochastic system. Okay. Okay, any questions? So far, I have just revised what we have done in the previous class. Any questions?
So I have a question. So the P we had, we used it in the sense as a probability as well as a rate, right? In the different, while we wrote the differential equation, it's a rate, right?
Yeah. So you're right that maybe I was not super careful. So the way to think about this is, so P as we have defined here is actually a probability in this specific case because P cannot be greater than 1. If P is greater than 1, this event doesn't make sense anymore, right?
Right.
Okay, just 1 second. I have to take one phone call. Please, sorry, people, I'm back now. Okay, so yeah, so here, it must be interpreted as probability. Okay, now, why so? Because you remember the way we described the rules, right? The way it works is I pick a site randomly, and then if it is 1, I pick a neighbor randomly, right? And then we implement this rule. So that means the time is already given to you. Okay, So therefore, given that instant and given the location, you are implementing such a rules with probability. So that's why P must be interpreted as probability for that time. Okay, now think about this. Now this P is for that unit, between, is for that unit time, right? So in that sense, it's also a rate. Okay, so this P is applicable for that, the time unit that we have chosen. So in that sense, it's also a rate. So that's a way to think about this problem, or to think about P. Okay, yeah. So this is where we are now. Here is one thing interesting. So let's go back to one interesting remark I want to make. Let's go back to the logistic model. Okay. So what was the logistic model? In this, continuous time, it was d n by dt was Rn times 1 minus n by k, right? So are these two models now this logic? What about logistic model, and what about the mean field theory of the spatial stochastic process I introduced? Do you see they're similar in some ways, and if so, how do parameters map? So what do we think of n as rho? Okay. So now if we expand this, we'll get Rn, right, minus Rn squared by k. Okay. So now what is Rn here? That's correct. That's equivalent to the linear term, right? So it will be 2p minus 1. So therefore, what is R? The intrinsic growth rate basically becomes 2p minus 1. Okay. And what is k? Okay, so now the coefficient of the quadratic term is p here, and it is r by k. Okay, that means that p must be also is equal to r by k, right? And we already know what is r in terms of p. So r is 2p minus 1 by k. So that tells us that k is equal to 2p minus 1 by p. Is it clear to everyone? So now what is interesting is that logistic model had two parameters, r and k, right? Now now this model has only one parameter. Okay, of course, that is partly because of the fact that we took birth rate as p and the death rate as 1 minus p. So that issue is there. Okay, now I will encourage you to redo the model, assuming that death was an independent rate parameter. Okay, that certainly, you think of it as probability again. I certainly encourage you to think about that and implement, redo the entire derivation. Okay, but at least for the way I described, which is not surprising that now there is a constraint here. So R and K are both defined in terms of P. Okay. No, but the point I'm going to make will not really matter how, will not really change even if we introduce a different parameter. So now here is, one thing to, I don't know how many of you noticed that logistic model has had a very weird feature. Consider the case r less than 0 in the logistic model. Okay, in this original model. Okay. So now how does the, this flow diagram look like? So here you write n dot on the y-axis, n on the x-axis. So how will this now look like? It's the invert, it was not an inverted parabola, it will be a regular parabola now because r is negative. It will look like this, right? So there will be two fixed points again, this one and this one, two equilibrium points, two population equilibrium. Right now, what about this? R is negative. We know sort of intuitively, and also if you look at it mathematically, it's fairly clear that this is a stable state, right? Any perturbation you make comes back to 0. Okay. So what about k, by the way? Is k stable or unstable? for r less than 0. Let's say I make a perturbation to the left of k. What happens? It decays. It decays down to 0. Okay. What happens if I make perturbation to the right of k? If I let's say population was at carrying capacity k with r negative, but let's say I have now made a perturbation to the right, more than added a few more individuals. What happens? It flows away, meaning the population size will increase. What do you think of this? Did you know this feature before? Had you noticed this feature about logistic model and R negative? I somehow vaguely remember somebody asking this question in the previous course. Isn't this a very, very weird feature? I mean, at least non-biological, right? It's not a biologically realistic feature. So this is, these kind of issues can arise for models that we directly write down at the population level. Okay. So although intuitively we seem to have made all correct steps, okay, when we wrote down this equation, right, by looking at the per capita growth rate and so on and so forth, we seem to have made all correct steps, okay, except that when r negative, but it still has this very weird feature, okay. So whereas that problem doesn't at all happen with this system, okay. Of course, this, because rho itself is now defined as proportion of filled sites on a landscape, you cannot make rho greater than 1. It actually imposes that constraint to start with. You should never even start, it's meaningless from mathematical and both biological point of view to even have a rho greater than 1. Okay. So, and those kind of issues are sort of intrinsically built in, and therefore sort of in some sense these kind of models eliminate the kind of weird features that occur in the phenomenological logistic model that we wrote. Okay. Any questions before I go forward? Okay. So today we will do a little bit more, to do mean field models, write down equations, we need practice. Okay. I mean, the only way to learn this is a lot of practice. Let us write down, more population model. Last time we discussed about the possibility of, facilitation. So what is a population model with facilitation? It should lead to increased birth rate. Okay, let's discuss what is facilitation. Okay, let's answer the question. Now, according to you, what is facilitation?
One species has a positive effect on the other.
Okay. So one so do we have to say one species, or is it better to say one individual? Is there a reason why you said one species has positive effect on the others? Why not one individual has a positive effect on it?
I think in this case, individual would be better.
Okay. Okay. Facilitation is a slightly more general term than mutualism, right? In mutualism, you often think of it as between species. Facilitation is broadly any positive interaction. It's not species specific. It's doesn't vary whether it's intra-specific or interspecific. Okay. So now how can this manifest? So go back to the way we think of population. It has birth and death, right? How does this influence the birth? So what should the positive impact do to the birth? It should enhance birth rate, right? And what about death? It should reduce the birth rate. Okay, now let us now try to incorporate this in our landscape model. Okay. Here is my little landscape. Which is a representative, which is, we should think of it as a small part where I'm zooming in a massive landscape. Okay, it doesn't mean there is nothing here. There are a lot of things that are, there. So now let's again write 1 zeros. I have written a few entries in the landscape, some bare sites and some occupied sites. Now, how do you think facilitation can act in such a landscape? So far we have described the birth rules as follows, right? If we have 1 0, 1 0 becomes 1 1 with probability P. Is that right? So you know that 1 0 can be this pair, right? It could be this pair, it could have been this pair, it could have been any of the pair. Let's say I have chosen this random pair. Now that has a probability P of becoming 1 1, right? Now here is the thing. Now let us look at, in contrast, this pair here. Actually, one can look at even this itself. There is no difference between this and this here technically. Maybe okay. Let me just redraw this. Okay. I didn't want that to be erased. So let me focus on initially on this. Okay. Make my leaf side line. Make my point. Let us assume this was also a 0. Okay. And then compare this 0 with this 0. What do you think is the, okay, no, not even this 0. Hold on for a second. So let me add more zeros here. Okay. Now, what do you think is the difference between this 0 as against this 0? Crowding. Say that again, sorry.
More live neighbors.
So okay, one can think of it as in two ways now. One is that of crowding, as somebody said. This is crowded by lots of ones, right? Around by. Okay, now if competition is the dominant force, then what do you think of the birth rate at this side versus birth rate at this side? It actually could be lower here because there is a lot of other sites. There's too much competition for resources, right? That's the competition angle. I will actually write you to do I will ask you to do an assignment question in the next assignment. How would you model crowding effects in the rules we have written so far? Okay. Now let's think of the opposite of crowding because we are discussing facilitation. Okay. So how do you think, is there also an impact of facilitation, possibly facilitation here for this side 0? Because it now has two neighbors here, which has, it has a higher chance of birth merely because this could germinate, this could germinate. That's not what I'm saying. Okay, that would still be the effect of this birth rule. Okay, that is still the same effect. See, we may randomly pick this site in our iteration process, and we may pick this to germinate, right? But this could also get picked when this was picked randomly. So there are two ways this cell can germinate, whereas this cell had only one way to germinate. So that is still the effect of the same birth rule, by the way. That is not different. There is an additional difference for this site. What is that? So it may be not very obvious. I have given a small hint here. So look at this, look at this here. This is now like a small cluster of individuals. The smallest cluster possible is really two, right? In the way we have described, this is the, two nearest neighbors are occupied, right? When two nearest neighbors are occupied, one can say that all of the neighboring sites could have a positive effect because they are both occupied and they facilitate the birth of other individuals. Okay, so if the facilitation is more dominant factor than competition, then all of these sites which are next to this pair has a higher chance of birth. Okay, that would be one way to incorporate the effect of facilitation. Okay, so if that is the case, then we have a new way of birth. So if there is a site which is, think of one is the pair, and then if you pick one of the neighbors of this 1 1 pair, we have 1 1 1. So let's say this event happens with a probability q. So this is an additional way to have birth when two nearest neighbors are occupied. Okay, and that's the birth effect. What about the death, by the way? So we of course already had a death rule. 1 becomes 0 at some probability 1 minus p. Okay, now again, this one is different from this one. In what way? In the sense that the none of the nearest neighbors of this one is actually occupied, whereas the nearest neighbor of this has an occupancy. Okay, so of course one can now say, what if more than one of it is occupied? Does it make a difference? We won't distinguish that possibility. We'll just say that whenever we have a pair, the pair has a lower chance of one of the individuals in the pair has a lower chance of death, and that we will assume will be modeled by this term. So 1 minus p was the death term, which was the density independent death term. Let's call this density independent death. What is this? This would be density dependent death. And in fact, it's a reduced death because of facilitation. Now, of course, there are, you may wonder what are the biological processes that causes facilitation. There are many. For example, there could be higher water infiltration. Okay, in a cluster. Okay, if it's were to think of this as plants, because we are really not modeling movement as much, right? So the birth is also just in the neighboring cell. So we could think of this as we are modeling some kind of a plant species. So therefore, one biological process that may lead to such facilitation is higher water infiltration in a cluster, and maybe lower water infiltration, lower evaporation due to shading. Okay, due to better shading in a cluster. Okay, and so on. Okay, so these are the biological processes that can lead to facilitation. So if you now include facilitation, this is one way how you can incorporate facilitation in birth and death processes. Any questions on this?
So this Q will be higher than P, right? Because facilitation here.
Does Q have to be higher than P? Is that what your question is?
Yeah.
Yeah. Does it have to be though? So you can say that any non-zero cube is a facilitation. Okay, so this is happening anyway by default. Okay, one can say that q is equal to 0 represents no facilitation, and any non-zero q is facilitation. So q need not be greater than p. And q can also range from 0 to 1 because we are interpreting it as a probability. Okay. Any more questions?
Did you choose 1 minus q because it's convenient? Because we can choose any number less than 1 to reduce the depth, right?
Yeah, absolutely. So for example, I could have also chosen D. Let's say we could do the generalization as follows, right? So this could have been D1. This could have been D2, where D1, D2 are less than 1, right? So yeah, it could have been done. So then this product then becomes D1, D2, right? So in principle, we can have now one value, one parameter P, one parameter Q, right? P is the baseline depth, baseline berth, and Q becomes the the facilitation driven berth, and then D1 is the density independent depth. D1, D2 becomes the net depth because of density dependence, but D2 is the reduced depth rate because of we can do it in that way, except that instead of 2 parameters now it becomes a 4 parameter model. So I'm trying to minimize the number of parameters in the model for algebraic simplicity. So just to for the algebraic simplicity, and I think you should also try out on your own. Does adding more parameter lead to more interesting dynamics? That is not possible. That's always an interesting question to ask, always an important question to ask. Are we limiting the possibility of various things that can happen by reducing the number of parameters? Of course we do reduce. The question is, do we reduce and lose out some rich dynamics possible?
So also for mathematical consistency, shouldn't the possible interactions, the probabilities of possible interactions sum up to like 1? Like, are we missing out any interaction here?
That's a very, very good question. You should work this out on your own.
Okay.
It looks like things don't add up, no?
Yeah.
Is that what you're feeling?
Yeah.
Please spend time and make sure you understand it.
Okay.
That's a great question. The thing is, I have not described all possibilities that can happen. Okay, now if you now think about all possibilities that can happen, you will find that they all nicely add up to 1. But I have not written them carefully enough. That's why you don't see them. No, but I haven't missed. So these 4 rules are complete. Okay, but I just haven't written on all possible steps. So if you now think of the introducing all the how do you actually implement it in simulation, you will notice that they will add up properly to 1. Okay, yeah. So if there are no questions now, let's try to do a mean field theory for this. Okay. Oh, I think I now have to do my standard kill the window, start again. So it's floating. Okay. Okay, again, we can now jump in, right? We can just write so again here P of A becomes of 1, right? That is rho. P of B is P of 0. That is 1 minus rho.
Right.
Oh, sorry, I forgot to show. Is it visible now?
Yes.
Okay. So, and then what about the transition rates? So these are the births. So what are the now two ways the birth can happen? 1 0 becomes 1 1, right? Okay. So the focal cell has to be 0. So what is the probability of neighbor being? So for the basic birth rate to happen, it happens with the probability p with one of the neighbors occupied. No, that remains same. So rho times p, that remains same. And then, but you can have the additional birth rate now. 1 1 0 can become 1 1 1. Okay. So how does that happen? So two neighbors must be occupied. Do you agree with this? So if one neighbor was occupied, the probability of birth is p. If two neighbors are occupied, that becomes rho times rho, right? Both of them must be occupied, and then you multiply it by q. That's the transition rate for t0 to 1. Now let's look at depth. So the first one is the density independent depth. It is the density independent depth. Okay. So of course the given site is 1 now, right? P of the given site is 1. I'm writing. Now this event happens independent of who is surrounded by this. So it always happens. So but with the probability 1 minus p. Just there's no density dependence here. But the second one is density dependent. Okay. Now if one of the neighbors is occupied, that's with probability rho, right? The depth is not 1 minus p, but it actually depth is 1 minus p into 1 minus p. Is that clear to everyone?
Will that be a minus or some,
Sorry?
like the debt should reduce, right?
Use now.
So should that be a minus, 1 minus p minus?
No. So this is also a death term. This is also a death probability. I'm just adding two types of death probabilities. So one way death can happen is this, other way death can happen is this. And I'm just adding the death probability by the baseline death process. And you can think of this as a death probability by the facilitation driven process. So it actually, okay. You are saying in the sense that it should be total should be less than this, is it? Is that what you're trying to say?
Yeah. I was thinking in that way.
I see your point. Okay. Okay. I think thinking from that point of view, you're right. Okay.
So 1 minus p should probably be multiplied by 1 minus rho, because for that baseline death to happen, you need like a zero neighbor, right?
That's also a possibility. Yeah. So I think that explains the problem. Okay, you're right. So this is actually true only if it's 0 1. 0 1 becomes 0 0 with probability 1. Okay. Hey, thank you, Bevan, for asking the question. It was Bevan, right? Very good catch. Yeah, it was a very good catch. So see, that which is why it's careful to write the rules. I think also, which is why I also recommend that you go back and do that summation of probabilities question carefully. Okay, you will make sure that you will get all the rules correct by doing that. So this must be multiplied by 1 minus rho. Great, thank you very much. Yeah, this is correct. Everyone on board here? Okay, great. So now we can write down the equation for how the density changes with this one. So first term will be 1 minus rho. All the birth will happen if the focal site is empty, right? And then you multiply it by this term, rho p plus, yeah, let me write this in a consistent way. P rho q rho square. This is the birth. This is the transition rate from empty to occupied by two different ways. And then if it is occupied, then there are two ways that can happen. The neighbor must be unoccupied, and in such a case, the probability will be 1 minus p. But if the neighbor is occupied, it will be this. Okay. This is the mean field equation for the model with facilitation. Okay. So shall we try to simplify this? So it's going to be a bit of an algebraic work to simplify. So since I think I know the answer, I will write down. Is that fine? I'll write down the answer. Okay. So d rho by del t. Please verify, because it's eminently possible that I make a mistake. So the linear term remains same, 2p minus 1 times rho. Why do you think the linear term doesn't change between the previous model and this model? There must be a very simple intuitive answer for this.
Because we're still using the original birth and death.
Yeah. So the original birth and death, they are still density independent, right? Okay. So so these are all additives, these are all additions that you can think of. So therefore, put together, they shouldn't really change. The linear term must not change. Effectively, it should not change. Okay. So that's the way. That's why the linear term remains same. Another way to think about this is the positive feedback effect is a density dependent effect, right? That will have rho square term. So any effect you see because of the facilitation will only happen in the rho square term, in the rho cube terms. It cannot happen in the linear term at all. Is that argument clear to everyone? See, it's like a positive facilitation is an interaction effect, right? So the interaction will always have higher order than linear term. Okay, so therefore they have to occur at a higher term. So this is the positive term. What about the negative term? You remember last time we just had minus p.
So the previous equation, dou rho by dou t, like shouldn't that term have a negative sign, not a positive sign?
The death must have what? Sorry.
A negative term, a negative sign instead of positive. Like
Oh, this one here, no?
yeah.
Yeah. Thank you very much. Glad to know that people are attentive. Thank you very much. Okay, so this is the linear term. So we also now have a quadratic term. Remember that we had a very simple quadratic term, p rho square, right? Now you have additional terms. Now it just becomes slightly complicated. I'll just write down. We have p minus q into 1 minus p. So I'm just looking at my notes and writing this, but I encourage you to verify this. Okay, and then the last term will be, can you guess what should be the last term? Should there be a rho cube term now at all or no? If it is only these two, do you think it should be a rho cube term? See, just look at the birth here, right? So birth has rho p and rho square q, right? Rho square, and we are multiplying this with 1 minus rho here. Okay, so there is a rho cube term from the birth, and likewise there is a rho. Is there a rho cube term from the death? No. There's a rho square term and there is a rho square term. There is no rho cube terms from the death. So only birth is, birth contributes to rho cube term. Okay, so and that happens to be just this. So this is the mean field approximation for the positive feedback model. Okay, I have to repeat the step. Okay. Okay, so what do you think can change now? So earlier we had a, when Q was 0, it's always useful to ask the following question. What happens if Q was 0? Do you go back to the old model? Doesn't change. What happens second term? This goes to 0, this goes to 0, right? We have P rho square. And what about this? This also goes to 0. And it's exactly what we had in the past. So which means that, setting facilitation to 0 takes us back to the original model, which is always one good way to check if I have made some silly algebraic error while doing these derivations. Okay, so that's great. It works fine with that. Okay, so now, of course, now you can solve for the equilibrium. How do you solve for the equilibrium? You just set the entire equation to 0. Now you can see that you can take rho as a common factor, and once you do that, so you have rho times 2p minus 1 minus p minus q into 1 minus p rho square minus q rho square, right? That is equal to 0. So you can see that one equilibrium remains same, which is that by setting just the rho is equal to 0, extinction equilibrium remains same. The other two we can find out by setting this entire thing to 0. This is basically a quadratic equation. There is no rho square here, it's just rho. Okay, because I have taken the rho as a common factor, we have a quadratic equation. So we will find two roots, for the quadratic equation. And then what do you now need to do? We will, you have to now take the derivative of this entire expression and plug the quadratic root solutions into that to find whether it is positive or negative, and that will tell you how the equilibrium will change. Okay, so I will leave it as an exercise. Okay, so please do the calculations. Okay, now intuitively, what do you expect? Do you think anything will change at all? So in the q is equal to 0 limit, how many roots do we have? We have only 2 roots, right? Rho is equal to 0 and the other one being p divided by 2p minus 1. Now we have 3 roots. What can happen when you have 3 roots? You have 3 equilibrium, 3 population equilibrium. So again, think of the following diagram. This is P, this is rho star. Absolutely, yes. This is what we had, right? We had this continuous transition from an extinction to a populated state, right? This was for Q is equal to 0. Weak facility, no facilitation term Q, right? Now, if this, what is, I'm just thinking about the possibilities. Because if you are just stuck in algebra, go back and think, what are you trying to achieve here, right? If you now plot as a function of p, you have now 3 roots. So one root will be always 0, right? And depending on the, you have to depending on the combination, you can now have 3 roots, something like this, right? You can have 3 roots. So when you have 3 roots, if there is the region of parameter space, when you have 3 roots, what do you think? What happens to stability? There are 2 possibilities, right? Remember, one possibility is that you can start with assuming this is stable. If this is stable, this has to be unstable, then this becomes stable. Alternatively, you can also have the following. This is unstable, this is stable, this is unstable. So basically, you can have multi-stability. So think about this, and keep this in mind, and then solve the algebra. Okay. So what features do you find in this system with facilitation, and see if it makes sense. How come introducing facilitation gave rise to multi-stability? Multiple stable state. Does that fit you with your previous intuition? What were the previous models where you had multi-stability? Think about those and make those connections. Okay. Any questions before I move on? Now, field approximation. Okay, that way you get even better intuition. Let's now forget the stochastic birth-death process. Let's do a very different model. Okay. So let me do a different model. It's called binary choice model. So this model has lots and lots of applications. By the way, let me just give you some terminology before I go forward. Okay, so this Q is equal to 0 limit. I think I already did in the previous class, right? It's called contact process. I have been defining in 2 dimensions. Okay, I have been showing you with the pictures of 2 dimensions. Okay, so it's called contact process, which is a very simple birth-death process. It was originally conceived in the context of spread of diseases in space. How and there P was the probability of infection. Okay. So there the implication was that unless the probability of infection is above some threshold value, the number of people with disease will not sustain the population. Okay, right? That would be the interpretation. Right? In this case, if the probability of infecting from one infected individual to the next within the lifetime of the within every interaction unit time, the unit time is half, if it is less than half, it would mean that that disease will not spread. Okay, so that was the basic idea with which it started. So it's called contact process, and and there are lots and lots of studies in the mathematics literature, because this contact process also becomes a very classic case of Markov process. You may have heard of what is called a Markov process. Markov processes are a class of stochastic processes that satisfy a very basic property that the current state depends only on the previous state and not what happened in the past before the previous state. Okay, other way to think about this, what happens, what's the state in the future. I have to take this call. Give me 1 minute. Sorry about that. There are lots. I'm on too many institute committees, and there's some very important calls I get, and I can't ignore them. So. Okay, so. So I think I was trying to make connections to the Markov processes. The idea of Markov processes are that given the state now, the future state will depend only on now, but not how I reach the current state. Okay, that's the idea of Markov process, and the contact process becomes a very interesting problem for mathematicians. There are lots of theorems and interesting properties that people have studied in both 1 and 2 dimensions, and you can answer many of them. It's like, okay, if I now populate, we know that, for example, in this extinction phase, right, between 0 and PC, there's an extinction phase, right? Now people ask questions like, okay, how do you, what is the exact value of PC? Okay, now so far what we have done is mean field approximation has given us a PC of critical value of PC to be half. But what is the actual value? So one can ask that question. We can ask another question. Okay, in this extinction phase, let's say if I start somewhere here, if I start with some density, what is the, we know it eventually will go extinct, but can you determine lifetime, average lifetime before it goes extinct, right? And then can you prove that it actually will go extinct? Okay, so on and so forth. There are lots of questions that mathematicians have asked and answered. Okay, and it's a very interesting problem. Now, for as you know, for Q greater, and also it turns out that the contact process, again, is just a bit of terminology, may not add much value unless you already know some stuff, is also belongs to a class, an universality class called directed percolation. Have any of you from physics background heard of universality classes? Have anybody from physics have heard of universality classes? No. Okay. No problem. The basic idea is as follows. You can construct millions of models. My choice of writing these microscopic fine scale models, right? If you were to start from scratch, you would write in slightly different way, and somebody else would write a slightly different way. Now can we say something general about all such models? Okay, so physicists come up with an idea of universality classes, which basically determines what happens to the behaviors near this, what is called a critical point of transition between one type of phase, which is an extinction phase, to a populated or an active phase. So in the vicinity of this critical point, what are all the behaviors? If the behavior, so the basic idea of universality class is that there are you can construct a large number of microscopic rules, but near the critical point, they will all behave very, very similarly. Problem that faces for difficult calculation, and I know somebody conjectured, I think it has now been proven that the contact process actually also falls into this important problem in physics called directed percolation. Okay, so anyway, in case you know, it's interesting. If you did not know, don't worry. Okay, so now let me go on to an entirely different model, binary choice model. So here is the idea. Let's say there are two choices to make. Choice one, let's call that A, and choice two, let's call that B. Okay, and there are agents who have to decide between A or B. Okay, each agent could go, for example, you could think of A as, if you are thinking of in the context of animal societies, you could think of agents as a colony of ants or bees, and they have to pick between two nests. And he has full information about where to go. And as you all know, these kind of social insects, they have a tendency to copy one another, and they now have to decide between these two binary choice. And then how do they go? Under what conditions will they actually achieve a consensus? Okay, so that could be one biological context. But there are also, it turns out that this broad class of models are also quite useful in human contexts. Many contexts, like where humans are deciding between two choices, and while they also have certain social interactions between humans. So broadly, there are many ways, and in fact, this model that I'm going to show, with some modifications, is also applied in the context of decision making in context like even in financial markets, where there are traders who are deciding between, should I invest in stock A or stock B? So there are many contexts in which this model has been used. Now let us write down the rules for this binary choice model. So let's denote. Now we have to make some notations. So now let's choose capital A and capital B itself to start off with. Okay. So maybe let me write this in a curly way to indicate that these are actually, some states or whatever. Okay. Let's say there is an individual who is in state A. There is some chance that this guy spontaneously decides at some rate S to move to state B. Okay, so an individual A spontaneously decides to go to B. Okay, now this is why this is not a, now can this be thought of as a birth-death model? No, for the very simple reason. You remember what happens in the birth-death model? This, while the death can happen, 1 can become 0, 0 cannot become 1. Okay, so this is not really, death cannot become 1 in the absence of other interactions, right? So this is basically what we call stochastic switching. So individuals stochastically switch between two states. Okay, but they also have a tendency to copy. So if an individual in state A interacts with individual in state B, that fellow decides, let me also turn into A because I have seen B is there. Okay, now of course this matter of choice, let's call this C to indicate copying behavior. Exactly opposite could have happened. So I'm going to write that in this fashion, although they mean the same, by the way. B could have turned, A could have turned into B, or B could have turned into A. So basically both of them are possible. Okay, and we assume symmetry. So therefore this rate as well as this rate, basically you can think of the reversible reaction A to B and B to A with equal rates. So this is called them, this is pairwise copying. Okay, extremely simple. Any questions on this? Don't ask me why the model is so ridiculously simple. This is just to illustrate how do we build mean field model for this. We can of course make more complicated, but ask questions about anything else.
So A plus B and B plus A, the probability C is like for both of them, right? Not like each has a probability C.
No. It's only for one of them. So whoever turned, so in this case, B turned A, that happens with the probability C.
Yeah.
Likewise here, A turned B, and that happens with the probability C. So in fact, here we should interpret it as you can also, because S and C are not really limited between 0 and 1. This actually could be really interpreted as rates now. But you can also limit this between 0 and 1, no problem.
Okay.
So you can actually say S and C are rates. Any other questions? Okay, let's write down how do we do mean field approximation now. Okay. Again, remember they're just two states, right? It makes our life easy. So we know that dPA by dt is PB times transition from B to A minus P of A transition from A to B. Right? So let's write down. So what is let's write down P of A as, let's give it a notation. Let's call this XA. What do I mean by that? Where P of A XA means it's a proportion. So probability of somebody being in A, right? So P of A is probability of somebody being in state A, right? And if that is XA, what does XA mean? XA proportion of individuals in state A. So that's the interpretation of P of A. Is that correct? So if there are n capital N number of individuals, okay, if the NA of them are in state A, then XA will be NA by N. Is that fine with everyone? So this is, in the previous case, rho was the proportion of sites which are occupied. Now it's the proportion of individuals in state A. It's sort of, basically same. Okay, that's P of A. So likewise, we know what is P of B. We know that P of B, we can denote that as XB, which will be nothing but 1 XA. XA must add up to 1, therefore, so this is just 1 minus XA. So far, fine. These are just definitions. Let us now write down the transition probabilities. B becoming A. So transition rate from state B to A. What is B for us? Yeah, B and A, So how can B become A? This one, a stochastic switch. This is like a density independent event, right? This happens independent of any interactions. And therefore, this is just proportional to S, right? Does everyone agree with this? That's just S. Okay, and how else can B become A? By this reaction, right? C times. So B becomes A when B interacts with A, right? So therefore, this becomes X times S times XA. Okay, is everyone with me? Oh, sorry. What did I just do? Yeah, separate events. Plus CXA. Is it fine? If it is fine, I will wait for 30 seconds. So only thing to keep in mind, how do we write this is, you are already in state B. Okay, now see what does it take to change. So if you're already in state B, the rate is now S, right? So this happening is rate S. Therefore, there is no other multiplicative factors here. If you're already in C, that means this is already there. If you're already in B, this is already there. So with C, I interact with A and then turn. So therefore, C times XA. Identical, by the way, there's really no difference. But I'm just doing it slightly more formally, step by step, which helps you in more complex cases also. Okay, this is TB to A. Can we write similarly TA to B? I mean, because the entire model is symmetric, this term must be same because it just corresponds to stochastic switching. And instead of B, you probably will have A. A, you have B now. Right? Now I can write this without even thinking. Okay. Now once I have done, now I can write down an equation for the full equation, master equation. So that just gives dxa by dt. What is P of B? That is XB S times CXA. So that is this term TB to A. Okay. Minus XA TA to B S plus CXB. Is that fine? So what we therefore have is xa dot is equal to s times xb minus s times xa. What happened to these two terms, cxa xb and cxb xa? They just got cancelled. So therefore xa dot is nothing but sxb minus sx. Okay. Now let us also write down an equation for xb. How will that look like? Xb dot is equal to, now that you know the equation, how should this look like? It should be s times xa minus s times xb. Also think, does it make intuitive sense? By the way, xa dot is basically stochastically switching from b to a. That is this term. The inflow is entirely because of stochastic switching from b to a, and the outflow is because of stochastic switching from a to b. Right? That's what these two terms mean. Always think what the terms mean. But what happened to the copying terms? The copying term just got cancelled. So both the outflow and inflow, because of the copying term, they get cancelled. So in fact, the rate equations have only the linear term entirely by stochastic switching. So these rules seem to have no implications on the mean field approximation. Okay. So we have this equation. Now here is, when you're writing this binary choice model, you often want to know the following: have they reached consensus, right? So consensus is an important question to ask. So how can you define consensus here, by the way? Let's say if they are equally split between A and B, is it a consensus? That's not a consensus, right? If everybody is in A, that would be consensus. If everybody in B is in B, that would be consensus. Okay. But if they are equally spread, that's not consensus. Okay. Now let's define a new variable called x, which is xa minus xb. So x will be 0 if xa is equal to xb, meaning they're equally split. X will be 1 if xa is equal to 1 and xb is equal to 0, right? Which means everybody is in minus 1 if it's opposite. But this represents lack of consensus, and this represents consensus. Okay, so it's useful. So we're not necessarily interested in A and B per se, but we want to know whether the consensus has been reached. Okay, so therefore let us define a new variable x, and let us find out the equation for x dot. So what will be the equation for x dot? It will be xa dot minus xp dot. Okay, so which basically means we subtract these two equations. So what do we get? So sxb minus sxa minus sxa plus sxb, that will give us 2 times s of xb minus xa. So this implies that x dot is equal to minus 2sx, because this is nothing but minus x. So this is the equation for the consensus variable. This is the mean field approximation for the consensus variable. Okay, is everyone happy with this? And we know the solution for this. This is just an exponential decay. Okay. So for large times, no matter what the initial distribution was, xt goes to 0, meaning lack of consensus. So what this means is the mean field model predicts that these simple rules of stochastic switch and a copying, pairwise copying, does not lead to consensus. Okay. So I will stop here. Let me know if you have any questions.
Is this concept of consensus useful in finding if, like, in a two species model, if they remain, if the two species remain at the end, like after a long time or not?
Two species model. I don't think I understood your question. Two species model, do they remain together?
Yeah, like will one of them like take over the world, or like both of them coexist?
A coexistence between two species. So how would you interpret? Can you interpret A and B as species here? Because they're switching back and forth, no?
Yeah.
You can't, right?
Mm-hmm.
Right? This is like now. So you can't think of it as a birth-death process. This is really could think of it as events happening in a lifetime where individuals are choosing between A and B. So this could, for example, literally mean, if there are two foraging sources, individuals are choosing between A and B in this
Yeah,
way.
yeah, I
That's an
understand.
appropriate, but birth and death, I'm not sure.
Yeah,
Or individual is choosing between two different types of flocks to join, maybe.
yeah. Like I was just like trying to see if from the part where you define the variable x, like will it be possible to use a consensus in that context?
I mean, okay, we have to change the rules though.
Yeah,
I mean,
the rules will change,
Uh-huh.
but I was just trying to see if this concept can be applied.
I mean, this variable transformation is a standard thing. A lot of people do it when we want to compare the two. Yeah, but if the rules change, yes, yeah, maybe. Yeah.
Okay.
Maybe you could then think of speciation and all, whatever. Yeah, there are simple Markov processes of speciation, and I think they might look like something like this in some limit. Okay. So I will stop here. Okay. So I'll see you all on Friday.